Which of these three numbers is the most random? If we're talking probability, then it's all the same. There's 10 digits and there's a 1 in 10 to the 10 chance you'd randomly come up with any of them. But us humans and our pattern noticing abilities will quickly point out that the first of them, 1, 1, 1, 1, 1, that's a pattern to the first of them. The second, do you see it? 3, 1, 4, 1, 5, 9, 2, 6, 5, 3, that's the digits of pi, the first 10 of them. The third one I just made up. I'm not aware of any pattern to represent it, just types of numbers on the screen. So how can we capture the notion that there's some types of patterns going on in the first two, but maybe not the third? Like, for example, I can just make computer programs for the first two. Like for 111, there's a very simple Python code. You plug this into Python and it's going to output 10 ones. And I could change the number 10 to a trillion and it would go off pretty quickly as well. For pi, well, this is the Chodnovsky algorithm. The details don't matter, but the point is it's some Python code, and if you tell it how many decimals of pi you want to compute, it's going to go and start chugging away and computing it. But for the third one, I don't know any shortcut other than just saying print the entire number. There's no pattern that I currently notice to leverage it. So the goal of this video is to talk about something called Kolmogorov Complexity. And loosely speaking, Kolmogorov complexity of some string y is the length of the shortest computer program that is needed to compute, to output that particular string y. This is a bit rough. We're going to make this notion a bit more precise momentarily. But a couple technical notes first. We're going to be working in binary, so this is not the number 100,000. This is the number 16. Because if I go and look along the bits, I've got 2 to the 0, 2 to the 1, all the way to 2 to the 5, which is equal to 16. And then since I'm talking about the length of the shortest program, I need a notion of length in binary. So like the length of the number 16, how many bits do I need to encode 16? Well, I needed 6 bits, 1, 0, 0, 0, 0, 0. And then final thing I'm going to do, I'm going to write that 6 as 5 plus 1. The 5 is relevant because 2 to the 5 is 16. But then I can rearrange that with logarithms to say that logarithm base 2 of 16 is equal to 5. So the length of our number 16 here is related to the logarithm in base 2. Since we're going to be using base 2 throughout the video, I'm going to drop the subscript every time, just write logarithm 16. So with that said, let's go back to our examples. Like, let's use, for example, the y, which is 1, 1, 1, 1, 1. I won't do it 10 times. I'm going to do it a generic n times. What's the complexity of that? We've seen this program that I can go and write to output it here. And this program, well, I had the number 10 when I was displaying it for you, but the number 10 could be like a trillion or as large as you wished. To encode a number like trillion, remember we just saw that you need something like the logarithm of the size of the number of bits to be able to encode it. So that's what the complexity is. It's the logarithm of n, and then plus a c. And the reason for the c here is, okay, so if the logarithm comes from you actually having to put in the number here in binary, all the other stuff in the program, that goes into the constant. It's a constant overhead. The print, the quotation marks, all of that. Maybe in one language you can write it shorter than another language, but it doesn't matter. It's a constant overhead. As the n gets really large, what's going to matter is the logarithm of n. The same is true for pi. I mean, it's a longer program. The constant overhead is longer, but at the end of the day, you have to input the number for how many decimals you want to do. And so the base 2 logarithm of n is once again going to be the complexity of the function plus that constant overhead for all the rest of the program. If I choose something, scare quotes, random, like the number that I made up here, it's not obvious that there is any shorter program other than just printing out the entire number. That would be the program. So however long it takes you to write the number, that's how long the program would be. And so it makes me think that the Kolmogorov complexity of y is just y plus a constant overhead to print it out. And I put random in the scare quotes here because maybe I hadn't given a precise definition. But what we're going to do later, when we define Kolmogorov complexity properly, is reverse it. And we'll say, well, when you have this property of k of y is at least y, then your string is going to be known as random. Now, one motivating thought of why I might want to be a little more precise about this, consider this paradox. The smallest positive integer that is not definable in under 60 letters. So the smallest positive integer not definable in under 60 letters. That is 57 letters. But hold on. If the smallest number not definable under 60 letters has just been defined, in a sense, in under 60 letters. We have a paradox. So we have to be precise about what we're talking about so we don't have to worry about things like this. Okay, so let's set the stage. I want to consider some inputs, and then I send them into a function if you're thinking mathematically, maybe a program if you're thinking with your computer science hats on, and you get out some output. Inputs map to outputs. In particular, we're going to be talking about binary strings for our inputs, binary strings for our outputs. So let's imagine you give me some function f. I have a notion of complexity. My complexity will depend on your f, so I'll write c subscript f to note that it depends on the f that you gave me. So the complexity of some output string, it's the minimum length of an input string. It's the minimum length of x, where f of x is equal to y. So if an f is specified, then I have a very concrete notion of the complexity. I like that part about it. It's just the minimum length of an input. But I don't like that it depends on the f. Like if I had an f and you had a g and they were different, you and I would be computing different complexities. That feels weird. I want sort of an objective or maybe a universal in some notion complexity to refer to. Nevertheless, let's use this for a few functions to build some intuition. Here is a terrible function to use. This function, if you input 0, it outputs 16. It just cherry picks it. If you input anything else, it outputs 0. Really silly function. Here's a second function I'll consider. For this function, it's just the identity function. G of x is equal to x. Okay, so let's compute out its complexity for a few different things. So if we do the complexity under f for this number of 16, remember 0 goes to 16. The length of 0 is just 1, so the complexity is short here. But for the identity function, you need to input 16 to get out 16. The length of 16 was 6. We'd seen that earlier in binary here. So this complexity is just 6. Bigger. Bigger, but they differ by a constant of 5. Just note that for the future. So for almost all the other values, the ones that are not 16 and then also not 0, well, that number is not even in the outputs of the function. And so we actually define these to be infinite. Like there is no inputs that output that particular y, so its complexity is infinite. But for g, again, it's the identity function, right? So it's just how long does it take to write that value in binary. The complexity under g of a particular output is just going to be the length of the output. So imagine you've got an f, I've got a g. How do we compare them? The term we're going to use here is that g minorizes f. And basically what it says is the complexity of g is smaller than the complexity of f for every value of y, but maybe with a constant overhead that we don't worry about too much. So it's not like the complexity of g is always less than the complexity of f. You can have that constant overhead, but it's at most a constant. There's never a multiplication by 2, there's never an exponential, it's just plus the constant. So going back to our examples that we computed here, which is which, well, for the 16, the f is better than the g. But the difference is only a constant, like 1 to 6, the difference of those is 5. There's a constant difference. That can be thrown in the constant overhead. But for all those other numbers, well, the one is infinite, the other is finite. That's more than a fixed constant overhead. So in this case, g minorizes f. So now we get to the big question. Is there a best possible f? Like, for example, is there an f that minorizes anything else you could possibly give me? That would be great. And the answer is a qualified yes. Yes, there is a best f, but only if we consider the class of computable functions. So computable functions loosely are ones where there is some computer program, some algorithm, maybe you could program it into Python, that is going to compute the outputs of f, every one of those inputs, and here's the crucial thing, in a finite amount of time. You don't have weird things like a halting problem where it may go on forever. Computable f's require this finite amount of time to compute them. One model of this is the idea of a Turing machine. We could do a whole video on this, but very loosely, I want you to imagine you've got some input, and Turing machine is like some black box, and it's going to go and take in this binary string as an input, and it's going to spit out some other binary string as an output. If our Turing machine is representing a computable function, if our Turing machine encodes a computable function, then this is going to be done in a finite amount of time. But the cool thing about Turing machines is that you can upgrade to something called the universal Turing machine. And what a universal Turing machine does is it eats not just normal old inputs like 1011, it also inputs entire other Turing machines. Like if you've got some algorithm that takes in inputs and puts out outputs, you could just encode that entire algorithm and spit that into the universal Turing machine as well. Both of those are going to go into the universal Turing machine, and what do you get out? You get out whatever the output was. Or to use this more symbolically, if you have an input X, Turing machine P, then you put both of those into the universal Turing machine, and what you're going to get out of it is just the output of the Turing machine, f of x. Okay, so we're going to use this universal Turing machine to come up with our best notion of a function that we'll use for Kolmogorov complexity. So the way this works is you give me some function, whatever function you like, whatever f of x you like. If I have a program that computes it, my universal Turing machine U is going to input both the program and the input, and it's going to spit out your output. And so now I can use this to define Kolmogorov complexity. Remember, I already had a notion of complexity for any function. I'm going to use that function U, the complexity of this U, the universal Turing machine of a particular string. That's going to be called my Kolmogorov complexity. So remember how we defined this. Remember, this was the minimum of the length of the inputs. So in our specific case, it's the minimum of these pairs. The inputs are now a program and an x. And we have this condition of computability where P is going to halt on input X and output Y. Just because we define something doesn't mean it's actually best. So what I have to argue for you is that the Kolmogorov complexity is best in the sense that this U function actually minorizes any other function that you might give. That's the key argument to make sure that this truly is the best. We'll do that, but one fun, quick technical point first. Suppose I have two strings, like an x and a y, 101, 001. I can do an operation called concatenation. And concatenation just juxtaposes them together and now thinks of it as one longer string. But there's a problem. If I get rid of my color coding here, and my labeling is to x and y, and a computer program reads this concatenation, it doesn't know which was the x and which was the y. It's lost sight of it. Like maybe the length of x is actually bigger, and the length of y is smaller. So how can we put these two strings together in such a way that a computer program can tell them apart? So the trick here is, let's take the first one, the 101, the x, and double it. It's now 110011. Now, I still can't just put them together and call it one string, because again, it's not obvious where the x starts and where the y ends if the beginning of the y has also got some things that are doubling in it. So here's the trick. We can put in what's called a sentinel. I'm going to put in an 01 in the middle. This pink 01 is not doubling, right? It was 110011, all doubles, but then 01 is not a doubling. So the computer program can look at this and can say, I see a whole bunch of doubling. Then I see 01, which is not doubling. That's the separator between x and y. And it will determine thus that x is the first of all the things that get doubled, ignore the sentinel, and then the y is the 001. This is not maybe the most efficient way to do this, but it works for our purposes. And the point is now I can compute out the length of our concatenation, which I denote, by the way, with these angle brackets. So the number of bits to encode x, you have to double that because you're doubling the x, so it's twice the length of x. You add the +2 for the sentinel, and then you have the length of y that just gets stuck in at the end. So we have a way to measure the length of concatenation. Okay, with that said and done, back to where we were. Remember, we were trying to make the claim that the Kolmogorov complexity was the best of all of them in the sense that this U that we have, that it was going to minorize any other function that you might give me. So here's a proof sketch. Imagine you've given me some function g that you think is better than mine. Okay, we'll see whether it is. And imagine that you have a program that actually computes it. You've got one of your computable g's. Then let's imagine you compute your complexity. You find the x that is the shortest input so that p of x is equal to y. You've got your complexity. So if I'm sitting here and I want to compute out the Kolmogorov complexity, I remember that it's always defined to be the minimum of the lengths of the inputs. If mine is the minimum, then it's certainly going to be less than one specific example of the example that came from the g that you were suggesting. So I say it's less than the length of this concatenation of p of x. So what we just saw in our technical preamble is that's less than twice the first thing, so less twice than the length of the program, plus the length of x, and then plus the 2 for the sentinel. But rearranging this, the length of x, that was your complexity. According to your G, x was the shortest input, so your complexity was just the length of x. And then what's remaining is just a constant. As you change the outputs y around, we're all talking about the same G, we're all talking about the same P, it's got a fixed length, you got this program encoded somewhere, that's all a constant. So the Kolmogorov complexity I'm using, it is smaller than your complexity, plus possibly this constant overhead encoding in the program. And so we have managed to demonstrate our claim. Okay, so at the beginning of the video I started throwing around the word random. Here I have my more precise notion. I'll say that a string y is what we call either incompressible or sometimes referred to as Kolmogorov random if the complexity can't be shortened from the string itself. The complexity of y is greater than or equal to y. And it's basically saying there is no program out there that can be shorter than just going and going for the entire string y itself. So this is going to be my notion of random. And a few things kind of follow from it. The first is that actually almost all strings are random. Like, for example, 99.9% of strings are going to have a complexity greater than the length of the string minus, say, 10, some small constant like that. So most strings are, actually incompressible, which is kind of interesting. The second thing that's interesting is we've talked a lot about computable functions, but the problem is that Kolmogorov complexity, we can find it out in some examples, but in general, it's undecidable what the Kolmogorov complexity is. That causes a lot of problems that we have to skate around as we try to do more advanced applications. And then third, I think it's kind of interesting, is that there's lots of incompressible strings out there, but specifically, there's an incompressible string for every possible length n. And this is going to be relevant in what we're going to do in a moment here. So basically, the argument for this is that if you want to think about strings of length n, well, there's 2 to the n of them. Right? In binary, there's 2 to the n possible strings of length n. Okay, so now you want to imagine that there's inputs that are leaving to these outputs of length n. But let's look at all the possible inputs. The number of input strings who have a length less than n, there's only 2 to the n minus 1 of those. And so if you want a Kolmogorov complexity less than n, you can't do that for all 2 to the n outputs by a pigeonhole argument. The most you can do it is for 2 to the n minus 1 of those outputs. And so at least one of them has a Kolmogorov complexity of at least that length of n. Now I'm a mathematician, so I wanted to use this Kolmogorov complexity to actually get a cool math result. I really love this slick proof. We're going to prove that there's infinitely many primes. A great result known for thousands of years with all sorts of great proofs, but I love this one coming from Kolmogorov complexity. And as so many of the proofs for this theorem work, let's prove by contradiction. Let's suppose that there's a finite number of primes. There's 2, there's 3, there's 5, and then there's some largest finite prime. I don't know what it is, we'll call it p sub k. One of the great things about primes is that you take any number like 18, you can write it as a product of primes. It's like 2 to the 1 times 3 squared, so 2 times 9 is 18. But you can do this in general. You take any number you like, any m, and it can be written as products of powers of primes. 2 to some exponential, 3 to some exponential, all the way down to pk to an exponential e sub k. So you have all these exponentials up here. So this is true for any m, but let's specifically focus on m's that are incompressible, and the length of m will denote as n when you write it out in binary. Remember, we just saw that for every value of n, there is one of these, so I'm allowed to suppose that, right? Any n that you choose, no matter how large you might wish, there's going to be an incompressible m that has that particular length. So m is incompressible, right? Its Kolmogorov complexity can't be shrunken down beyond just the n. But the big idea is this. If I look at the exponents, well, actually, the exponents alone will give a shorter description of m than the value of n that we're presupposing. That is, we're supposing its complexity can't be brought down below n, and we're going to argue that the exponents will allow us to bring it down below n. That's going to be our contradiction. A lovely proof idea. Okay, so here's the mechanics of it. If I take m, I can take the logarithm in base 2 of both sides. Remember, the logarithm of a product is the sum of all the logarithms. Then another log rule, all those exponents, they come out the front. So if I focus on like one specific exponent here, a generic EI, well, logarithm of m is equal to product of a lot of stuff. If I just take one of the terms, we get an inequality, right? So the EI is less than or equal to logarithm of m, which is just n. So we define the length of m to be equal to n. So if EI is less than n, the length of EI, again, our trick that we've seen over and over in binary here, is less than the logarithm base 2 of n. What I'm really interested in is all the exponents. So what I want to know is the concatenation of all of the exponents, E1 down to EK. Now, we'd previously seen this concatenation trick, like you double the first one, you put in the sentinel, then you go for the second one. Okay, we can do the same kind of idea here for a concatenation of k things. Double, sentinel, double, sentinel, double, sentinel, all the way along. So nevertheless, if each one is log n, there's k of them, you take 2k. You have to have that doubling that's less than 2k logarithm of n. Okay, so back to where we were. Remember, we supposed m was incompressible. Its complexity cannot be smaller than n. It has to be bigger or equal to n. That was our assumption. We can always find one of these for every single n, so we have such a value. But what we just showed was that this string of exponents, that its length was less than n. So the Kolmogorov complexity is both bigger than n and less than n. We have a contradiction. Our theorem has proved there's infinitely many prime numbers. Now, we are just scratching the surface of where you can go with Kolmogorov complexity, but I hope you enjoyed this introduction. We're going to be using this in a video coming up a little bit later. I hope you're excited for that one. Regardless, if you have any questions, leave them down in the comments, and we'll do some more math in the next video.